Hey everyone, welcome to The Explainer. If you've ever stared down a physics equation and just felt this immediate wave of anxiety, trust me, you are absolutely not alone. It is incredibly common to view physics as this intimidating giant mountain of complex math. But today, we're going to reframe that entirely. Let's dive right into this. We are going to start treating physics not as some grueling math test, but as a universal language. And just like any language, once you understand its basic alphabet and its grammar, everything else just starts to make perfect sense. Here is our quick roadmap for today. We'll be looking at the language of physics, the 7 pillars, precision and uncertainty, filtering significant figures, the DNA of dimensions, and finally, the perfect measurement. All right, part 1, the language of physics. To really understand why this language exists at all, we first have to understand the fundamental necessity of units and the sheer danger of what I like to call naked numbers out in the real world. Let me just ask you something directly. What does the number 287.5 actually mean? Seriously, take a second and think about it. Without any context whatsoever, it is utterly meaningless. It's just math floating in a void. And that right there brilliantly illustrates why a physical quantity always requires two things: a magnitude, your number, and a unit. Because if I just say 287.5, what is that? Is that the distance to the next town in miles? Could it be the diameter of a pipe in millimeters? But if we give it the unit of centimeters, suddenly it makes perfect sense as maybe the width of a small room. The unit is the thing that actually grounds the math into our physical reality. Moving right along to section 2, the 7 pillars. So we know we need units, but whose units are we using? Exactly. To solve the whole naked numbers problem, we use SI units, the International System of Units, basically our universal alphabet. Now, for the longest time, humanity actually defined these units using physical artifacts. A kilogram was literally a block of metal just locked away in a vault in France. But here's the kicker. Metal degrades. So in this absolutely fascinating revision back in 2018, scientists completely shifted the definitions away from physical objects and pegged them directly to fixed, unchangeable universal constants. And here they are. These are the 7 fundamental pillars of the physical universe. Literally everything you could possibly measure in your everyday life boils right down to these 7 base units. Let's look at 2 major real-world anchors: distance and mass. Distance, which we measure in meters, is no longer based on a random metal rod. It's now universally defined by the speed of light. Crazy, right? And mass, measured in kilograms, is now permanently anchored by something called the Planck constant. These are the flawless, unshakable letters of our universal alphabet. Which brings us to section 3, precision and uncertainty. Now here is where things get really fascinating. See, while our units are theoretically perfect and constant across the universe, the physical tools we actually use to measure them, well, they're not. Every single measurement you take out in the real world carries an element of human limitation. Because no tool is infinitely precise, every measurement will always include a little bit of human error. There will always be an uncertain digit. And that brings us to the whole concept of significant figures, which is basically how we honestly communicate our uncertainty to everybody else. Let's look at this everyday example. Imagine you're looking through a magnifying glass at a standard ruler. That 1.6 centimeters? That is absolutely reliable. The mechanical hash marks guarantee it. But what about that final 2 at the end, making it 1.62? Well, that is just a human estimate between the lines. It's an uncertain digit. So your significant figures are simply all of your perfectly reliable digits plus exactly one uncertain digit. Make sense? Okay, section 4, filtering significant figures. If we constantly have these uncertain digits just floating around, we obviously need a solid set of grammatical rules to do the math without, ruining the truth of our measurement. We handle these numbers almost like we're running them through a digital filter. Digits 1 through 9, they always survive the filter. Zeros trapped between numbers, they survive too. But trailing zeros, they only survive the filter if there's a decimal point there to prove that those zeros were measured on purpose. This filter actually cements the grammatical rules of precision, so scientists all over the world are reading numbers the exact same way. And when we do the math and end up with way too many uncertain digits, we use this visual flowchart for rounding. Now, most of this is exactly what you learned back in grade school. Greater than 5 rounds up, less than 5 stays the same. But check out the middle trek. There is this incredibly intriguing rule for dropping an exact 5. If the digit right before the 5 is odd, it goes up. If it's even, it stays exactly the same. It's this beautifully elegant rule that actually prevents statistical bias when you're analyzing thousands of measurements. Pretty cool, huh? All right, let's pivot to section 5, the DNA of dimensions. So we've talked a lot about numbers and units. Now we're going to shift our focus from the numbers themselves to the underlying concepts, the dimensions. In dimensional analysis, the magnitudes, those numbers we just spent all that time on, are completely ignored. We only care about the core physical nature of the thing we are studying. I mean, whether you are talking about the initial velocity of a baseball, the average velocity of a car, or the change in velocity of a massive rocket, they all share the exact same dimensional DNA, length divided by time. And this brings us to a massively important rule called the principle of homogeneity. Look at this balance scale analogy here. It beautifully emphasizes our focus on real-world mass concepts. In physics, trying to equate velocity and force is exactly like trying to add apples and oranges. You just can't do it. An equation is only valid if the dimensional DNA on the left side of the equal sign perfectly matches the right side. It's basically the ultimate lie detector test for any scientific formula.
Finally, section 6, the perfect measurement.
So we've got the alphabet of our SI units, the grammar of our significant figures, and the underlying DNA of our dimensions. Let's bring this whole thing together. Take a look at the anatomy of a perfect measurement and how these elements combine. We have our precise magnitude, handled correctly with scientific notation and significant figures. We have our alphabet, composed entirely of universally unchangeable SI units. And underlying the whole shebang is the dimensional DNA that validates the entire concept. When you combine all of these things, a measurement is no longer just a naked number. It becomes a complete, grammatically perfect sentence in the language of physics. By looking at physics through this kind of lens, hopefully it feels a little less like an impossible math test and a lot more like a logical, structured language that you are entirely capable of speaking. So, I'm going to leave you with this final thought. If our entire infinite physical universe translates into just 7 fundamental pillars, what other complex, intimidating systems in your life are just waiting to be decoded? Thanks for exploring with me today. Keep asking those questions, keep looking for that underlying structure, and I'll see you in the next explainer.